just talking about simultaneous time-lapse processing, and the goal is to improve repeatability of the seismic data. A little introduction. So why would we do time-lapse processing? Talk a little bit about traditional time-lapse processing, and then contrast that with what we're calling simultaneous time-lapse processing. And also talk a little bit about a repeatability metric that we use throughout some stages of the processing called NRMS. And use an example from recent processing that we've done on Goose Coupe and Montney Shale with a focus on 4D shear wave splitting analysis, basically to characterize fractures. So why 4D time lapse? Well, the objective is to determine the changes occurring in the reservoir as a result of any activity such as production or fracturing, hydraulic fracture, propping of fractures, injection of heat, pressure, water, gas, and so on. All these things cause changes in the seismic signal. And basically we want to understand the changes in the reservoir over time. So we're interested in the changes in the signal as we repeat surveys. And we compare these repeated seismic data sets and integrate information from other sources, such as microseismic, production data, well logs, and so on. In order to do this successfully, the data should be acquired quite carefully. Processing and interpretation also has to be done carefully. If you want to reveal any subtle changes in the reservoir. So traditional flow, we take baseline survey, monitor survey, process them individually. At the very end, cross-equalize the stacks, and then look at any differences if there are any left. So this is potentially the cross-equalization step could potentially throw away a lot of useful information that might be in that signal. So another approach is to combine your baseline and monitor up front. Do as much of the processing as you can simultaneously. And then at the end, separate out your baseline and monitor, and then compare the differences. So as I was saying, simultaneous time-lapse processing involves processing all the data sets together as one data set as much as possible. It's good to extend the concept of surface consistency in your flows to source-receiver consistency. So each baseline, monitor, vintage, so on would have a unique identifier for a trace, even if it's co-located. So this hopefully enhances your time-lapse repeatability. And along the way, you can do some checks, which would involve many things, but a quantitative measure here would be NRMS. We look at the RMS of the difference between two windowed traces, stacked traces, and then normalized by the RMS of their average. So this was due to Calvert and others in 1905. That's a common measure of repeatability throughout the industry. Usually it's reserved for the end of the processing. But we use it at some stages throughout the processing. So a little bit of background on what this is measuring. It's trying to it's supposed to get a measure of how similar two traces are. So first thing you do is look at a common frequency band where you think your good data resides, and a time window within what's called the interpreted no change zone. So there should be some region in your seismic that isn't changing over repeated surveys. That could be above the reservoir, below the near surface. The values range from 0 to 2 for NRMS. If you have two similar traces that are aligned with time, then the NRMS goes to 0. The more similar they are. If you have two identical traces but with opposite polarity, you get the worst NRMS value, 2. And it's very sensitive to time shifts. So if you have identical traces that are slightly misaligned in time, you could get fairly large NRMS values. So in a way, it could lead to false negatives. So there is some work being done by others, Catillo and such, perhaps other measures, something like signal to distortion ratio, that is very similar to NRMS, but does some cross correlation first. So it's probably a better measure of similarity of traces, although it doesn't care so much if they're not quite aligned. So part of our simultaneous amplitude-friendly time-lapse processing is to calculate these NRMS errors. There are lots of other QCs that we do along the way, but this is one of the newer ones. And we're just comparing multi-vintage stacks here with NRMS. Of course, as I was saying, we carefully choose the time window and the frequency band. Window should include no change zones, entirely above the target zone if possible. And the frequency band should capture the majority of the signal and minimize the amount of noise that you're including. So just go over a few of the main steps that we might look at this. So the evaluation of simultaneous processing. First break picking. So first thing you do is prepare your data so that as much as possible you make it look like it came from the same experiment. So some pre-processing is typically required on the first breaks before you do your first break picking. Geometrical spreading correction, and then one thing we do is use a common refraction status model, which is possible provided you've done a good job with your first breaks. So we use the same near surface model. That tends to give one of the biggest uplifts in repeatability. And combine that with another source and receiver consistent amplitude correction gives a pretty good uplift. Other steps: ground roll removal, pre-decon noise attenuation, source receiver consistent decon, source receiver consistent amplitude correction again, and velocity and residual statics update. So here we tend to use a common velocity model, at least initially, and common residual static solutions. And this tends to give another good uplift in repeatability. And then some other steps: post-decon, noise attenuation, CDP trim statics. This tends to be a pretty mild trend. Post-stack noise attenuation, and pre- or post-stack migration. So some factors to consider. What we typically do is something called fold matching, where we only combine repeatably acquired data, which in this sense means using co-located shots and receivers as best as possible. So if the shots and the shots are too far apart from each other, the receivers are too far apart from each other, then we'll discard them. So we're trying to maximize the acquisition repeatability at this stage. If required, you could try interpolation, try to boost this up if you're throwing away too much data. As much as possible, we produce one common processing model, or parameter for each of the steps involved for the baseline and the monitor data. So in this sense, you get sort of a happy medium solution, which wouldn't necessarily produce the best structural stacks, but it's a better way to try to extract the 40 signal. So you should really expect separate deliverables here. One where we're not too concerned about fold matching and that kind of thing for the structural interpretation component, and another with simultaneously processed data, as I'm speaking about here, for the time-lapse analysis. So by the time we're done, cross-equalization is usually very negligible at the end of the processing. It's something that we take care of throughout the processing, rather than waiting to the end. Another thing to note here is that has a lot in common with 3D merging. In some ways, so the distinction really is kind of blurred between what you can do with 3D merging or simultaneous processing. There are some subtle differences, but there are enough things in common that you can port them over. So maps filtering on the overlaps, phase and statics, common refraction statics model, and using a common velocity field and residual statics. So I'll talk a little bit about a case study. This is working in conjunction with Chris Steinhoff from RCP. This was published in January's Leading Edge. An example from Mont Michel and Pouce-Coupé. So, Pouce-Coupé is in northeast Alberta, I guess, very close to the BC border. It's considered an unconventional reservoir. So there's baseline and two monitors shot pretty close together in time. And in between surveys, there was hydraulic fracturing activity. So along this well here, this is phase 1, and phase 2 is right here. The frac stages are indicated by these pentagons here. So the shot for maximum repeatability in line, the receivers are fixed in place for each of the surveys. Just give you a sense for what the raw data look like. Here's the raw P-wave shot gathers from the baseline. Monitor 1, monitor 2. Back and forth a bit. And then following the 7 slides, I'll show you some examples of trace triplet, what we call trace triplet displays, where we take, say, the baseline, monitor 1, monitor 2, and take traces that are co-located and put them together side by side in the displays. The first 2 slides show some repeatability uplift after refraction statics correction and source receiver consistent scaling. And we found that this gave the largest repeatability uplift, as I was saying earlier. The next 5 slides would focus more on converted wave processing. So we're looking at repeatability changes as we progress through the processing. So here are the raw shots. Got these trace triplets that I was talking about. Baseline, monitor 1, monitor 2, and so on. And then after common refraction, static solution, and source receiver consistent scaling. If you look at this, you can convince yourself that the repeatability is improving. I'll jump right into the converted wave trace triplets. Again, these are shot gathers. So starting with raw data just after geometrical spreading corrections. Compare that to some band-limited surface consistent amplitude scaling. Fair bit of uplift there already. Compare that to after receiver static corrections. Not so much repeatability noticed here. Obviously some time shifting, but at least they're all shifting together. And after some singular value decomposition, ground roll removal, and what we call TFAN's high amplitude noise attenuation. This is time frequency adaptive noise attenuation. Does a pretty good job of removing that low frequency, high amplitude stuff. And then after another pass of surface consistent, or actually source receiver consistent amplitude scaling, very little change there. very subtle changes. So another way to look at repeatability is by looking at NRMS maps. Here I'll show 4 slides with NRMS maps at the reservoir level, so these are time slices. So the beginning of the processing, hot or cold colors are 0, hot colors red. So you're looking to move towards the greens and blues here. Good NRMS values would be somewhere between 0.2 to 0.4. So this is after surface consistent scaling. Fairly big difference just from that. And then after after our final interpolated final stack, colors are somewhat washed out on the screen here. And then after some post-stack noise attenuation. Pretty decent repeatability values in this range. Here's a comparison of some original processing that was done. Then we reprocessed sensor with simultaneous time-lapse processing. So NRMS values are pretty high here and spread out way up to 1.4. We managed to get that down to around the 0.2 level with a smaller spread. Why such a big difference? We don't know for sure, but we made some improvements in converted wave processing. Could be different processing capabilities, methods, tools. They probably didn't use a common receiver or fraction statics model. Different velocity models, trim statics, and so on. Maybe some information was lost post-stack with cross-equalization. We found that the receiver azimuths needed some correction, and this makes a big difference in your results. And in particular, it really has a drastic effect on shear wave splitting analysis. So here's some shear wave splitting analysis attribute maps from baseline monitor 1 and monitor 2. And we're looking at very subtle changes here. This is 4 milliseconds of delay, which is unheard of for a single vintage shear wave splitting analysis. So we're looking at pretty subtle changes, but what we're seeing here is that, maybe I should explain this map a bit. These little needles here, which you may or may not see, are pointing in the fast direction of the shear wave splitting, which is oriented along fractures, or tends to be oriented along fractures. The color in the background tells you what the time delay is between the fast and slow shear modes. So what we're finding is the orientation isn't changing very much. It's changing very locally, but what's changing, more obviously changing, is the time delays. So why is that? Here's some another analysis that was done by Chris Steinhoff post-stack on the PS1 volumes, or PS1 and the PS2 volumes, which is just the fast and slow shear wave volumes. Took the baseline, did some time differencing on events that were interpreted, and then did the same for all 3 surveys. And on the bottom here, we're looking at the changes between monitor and baseline, monitor 2 and baseline. And what Chris found is there was some correlation between increased time delay and production. So his conclusion actually was that what we're seeing is an indicator of how well the fractures were being propped open. So open fractures leads to bigger time delays between fast and slow shear modes. So that's pretty interesting. Labeled here is some production data from spinner data. I believe this well was more productive than this well, but we don't know what the actual quantities are. But we do know what the total is as a percentage of the total production of each So it's interesting to compare that to the fault mapping interpretation. Nice fault running through there. You can see that. You can see these actually right there. On this map, you can see something kind of growing along here. Right, so integrating all of this, all the pieces of the puzzle here, we've got a time-lapse workflow that isolates seismic changes at the reservoir, looking at converted wave data, which is very sensitive to anisotropy, which in turn here means fractures and faulting. By the way, this was interpreted on the fast volume. Chris said that he was unable to do this interpretation on the P-wave data. So it's fairly well known that shear wave data is more sensitive to fractures and faulting than P-wave data. So 4C or time-lapse shear wave splitting analysis before and after fracturing treatments, we think is an indicator of propping of fractures. As an aside, it's also an indicator of cap rock and sub-rock integrity and useful for density inversion as you get bigger offsets or bigger angles of incidence with converted wave data. Bring in microseismic monitoring so that you can get a map of your fracture network or your active fracture network. Some production histories at each frac stage, spinner data, for example, here. How does all of this relate? That's the interpreter's job. So, to conclude, present an improved time-lapse workflow, where the traditional workflow aims to produce the best stacks and gathers, whereas the simultaneous workflow aims to extract most meaningful differences between the vintages. So it's after the 4D signal. We introduced the quantitative QC using NRMS as a repeatability metric throughout the processing sequence. Went through an unconventional reservoir monitoring example, where we used simultaneous processing and other improvements to yield subtle changes in shear wave splitting attributes. And in the end, this was correlated to cropping of fractures. And I also mentioned that the distinction between time-lapse processing, the simultaneous processing, and 3D merging is quite blurry. There is a lot in common there. And also, for future improvements, I think we'll look at signal-to-distortion ratio as introduced by Cantillo in 2012. It's less sensitive to time shifts than our NRMS, but captures shape similarity just the same way. Could be more diagnostic than NRMS at early stages before your statics are resolved. Lots of people involved with all of this work. Thanks to Talisman Energy and David Minko, who's here. Eric Anderson and Heath Peltier for show rights and collaboration. Also Tom Davis, Chris Steinhoff, and Heather Davies at RCP at Colorado School of Mines. This data was processed for that. And Sensor Geophysical, especially Rodney Cousins, Julia Popov, Ken Lazarko, and Robert Pike. Lots of input and processing. And Xinjiang Li, he's actually the first co-author on our first break article on this topic. So this is a follow-up of his work, really.